back, folks. This is part 13, Laminations, episode 1, and it's a section found in API 579 and how to deal with these issues. So, first of all, we're going to start off with the definition. What is a lamination? Secondly, we're going to look at, how the manufacturing process creates laminations, because it doesn't really occur during when it's being in service. It's a result of manufacturing. And the effects of laminations, how does it affect the integrity of the component that has laminations? And we're going to look at the evaluation of risks. It's interesting. Just like dents, for piping system, pipeline folks have some very interesting um, ways of evaluating these risks very quickly. And also, we're going to look at part 13, assessment limitations, when we can't use it, when we can. And part of one of the criterion is if it's in sour service and there's a lot of hydrogen charging going on, and that will create blistering, and then that will limit the assessment, and then you'll have to include several other parts. Next, we'll look at the inspection and monitoring. Look at the definition of a lamination. To the diagram to the right, you can see 3 laminations in a steel structure in a plate. And basically, a lamination is defined as layers in a steel plate that do not fuse together. It results from the rolling of a plate during steel manufacturing, and it's in the direction of the gray lines where it's been rolled. It's located in the plane of non-fusion of the interior of the steel plate or on the edges. So it's typically found right in the middle of the plate or in the edges. And it exists, on one or more planes. Manufacturing of steel plate is done by cold or hot rolling. The diagram that I show over here to the right shows it being rolled from a thicker part to a thinner part. And when there is a flaw in that part, it can get elongated along the direction of the grain. So it's a plate is produced by the process of hot or cold rolling a thick slab, and or hot forming or cold forming is another way of saying the same thing. And it's resulting of porosity or inclusions that are trapped within the slab, and these can be like impurities like sulfur and tying up the sulfur, the sulfur manganese, for example, and they're elongated along the direction of rolling. And if the impurities are greater than must be greater than 5.5 microns, and includes these impurities include like things like sulfides, oxides, silicates, nitrates, etc. Of steel plate. So the higher concentration impurities migrate to the center of the slab as cooling occurs from inside to outside. The second thing is that there's a separation of the layers of metal at the exit of the roll process, and this is known as laminations. The third thought is older steel making practices have less controls and less industry specific practices, and so they usually have more laminations than newer steels. And that's something to really consider when you're looking at older vessels. They would recommend that you do more work with UT if you're going to be, attaching attachments to that part of the steel structure or nozzles, and that's something to consider. Now let's look at the effects of laminations. First of all, it can interfere with UT examinations of welds. Secondly, it can reduce the strength of the plate and reduce the allowable bending stresses. It can reduce the allowable compressive stresses, and it can reduce the through thickness stresses because the parts are not the plate is no longer fused together for the additional strength, so it can weaken the allowable stress of the part. So the voids can trap hydrogen, free hydrogen that can migrate into the components, causing blistering in wet hydrogen sulfide service environments. So let's look at the evaluation of the risks. In the pipeline industry, and in particular, there's a number of risk mitigation methods or ways to quickly evaluate the piping or the pressure vessel or equipment. Um, First of all, planar laminations, those are the ones that lie parallel to the pipe or pressure vessel wall. They they remain on a single plane across in the middle of the pipe or plate are typically considered by rule of thumb generally acceptable. But a medium level risk is if we have like a sloping lamination, and this is where we would typically the light would come on and we would be typically looking at that as an evaluation. So they are inclined towards the interior external surface of the pipeline and they impose a high risk. Now we have the third one, which is lamination with cracks or metal loss. This one is a higher risk, and typically, even without evaluation, you would be looking at a repair. Laminations interact with other significant anomalies, such as metal loss or cracking, and like I said, dents. They always, if they find cracks, it's got to be yanked, repaired, and removed. About the evaluation of risks. The laminations may not be objectable, okay, or an issue if, for example, if it's internal pressure only and the plate is not subject to, tensile membrane stresses from internal pressure, or, we're far away from um, structural discontinuities. When we look at the examples that we'll do in the next videos, you'll see the effect of structural discontinuities and the precautions that API takes to consider them. Laminations, that are away from structural discontinuities where local bending and stresses or concentrations can occur. So essentially, if you're far away, you're not going to get local stresses or concentrations, and relatively speaking, that is considered to be a low risk. At the assessment limitations that API lists for doing the fitness for service part 13 assessments. First of all, the assessment is designed for pressurized components for lamentations. It's not been designed for structural lamentations, and that's very important to consider. The next thing is that part 13 excludes, HIC, hydrogen-induced cracking damage. That's another part in the fitness for service, and we have videos on that. So if you're curious, take a look. We also excludes SOHICs, so that's stress-oriented hydrogen-induced cracking damage. And lamentations cause no bulging of the metal surface. So if there's any kind of bulging, then bets are off. You have to go to another part of the assessment. So if there's no, of course, um, just like we talked about earlier, there can be no cracking in the through thickness direction. Okay, and these laminations aren't all linked together. Hydrogen service. So here's a sort of a classic diagram of hydrogen being generated here. You can see this diagram here. These are the hydrogen bubbles, and that's the chemical reaction that can occur, right? Where free hydrogen is generated, and right here, and then it can dissociate it out as bubbles. And in steel, we have the issue of monatomic hydrogen, which we have a video early in our library for your uh, preview. So let's get to this. So basically, hydrogen charging, just as a reminder, is when H2S interacts in the presence of water, producing free hydrogen that can penetrate the walls of a pressurized component, causing damage. So if this is the case, then you need to follow the requirements of Part 7 and refer to also to API 571. There's an example of wet hydrogen surface that you can have a look at. And the limitations can be assessed also by Part 13 if there's um, no hydrogen charging. It's a non-hydrogen charging environment, just as a reminder. Next one we will talk about is inspection and monitoring. So the primary technique for lamentation is by using ultrasonic through body UT inspection, which is quite easy to do. I typically use that a lot if I'm cutting holes in a nozzle in an existing pressure vessel, and especially if it's a very old vessel or an old tank, and I don't know what the quality is, and I don't want any surprises during welding. Um, Typically, if we do see laminations, our first is to avoid them because it adds complications. It's more difficult to weld, and then it's more difficulty to confirm that the by UT detection methods to make sure that the that the weld has been done properly. And so those are some things that to consider. So that pretty much concludes our discussion and introduction about the assessment of laminations.